All right, now let's go ahead and let's consider this function, which is h of x is this massive, indecisive piecewise function. I mean, literally, look at this thing. I want to be this if we're less than 1. I want to be this when we're at 1, but I want to be this if you're between 1 and pi over 2. In case you're curious, pi over 2 is like kind of like 1.5-ish. And then I'm going to be this between pi over 2 and 2, and I'll be this when I'm above 2. Wow. Okay, fine. Really weird, but let's go with the punches. So let's go ahead and evaluate the following. Let's evaluate the limit as x approaches what? Pi over 2 from the right, guys, right? Pi over 2 from the right of h of x. So now I have to be really mindful as to which piece to hone in on, okay? If I'm coming from the right of pi over 2, do we recognize this won't do it? Because this is numbers which are between 1 and pi over 2. Like if you read left to right, it's from 1 up to pi over 2. So that would be the piece that I would use if it wanted the limit as we approach pi over 2 from the left. But no, I want to come at it from the right, just a touch above pi over 2. So it's going to be this guy. Yes? Now this is where things get weird, and I want to point this out because this just shows up as sort of a weird ancillary way of doing these problems. What will happen is if you try, your best bet for the limit is always found by plugging the number in. If you try to plug the number in and say, well, the limit as x approaches pi over 2 from the right of h of x, and again, this notation stuff, if you can write that down and make it look sexy, it's going to help you tremendously. But regardless, the limit as x approaches pi over 2 from the right of h of x, you'd say that's just the tangent of pi over 2. Crap. Doesn't exist. So here's what you got, right? Because we know from trig that that's where we got ourselves an asymptote. So what I recommend you do is as follows. Try to pull out of nowhere the graph. Watch. Look, the graph is going to be your best friend. For tangent of x, do we agree we have negative pi over 2? And I'm going to write this up here, pi over 2, right? Tangent's a little snaky guy, and it does like this, right? So look at that graph. If you were to trace it as it heads to pi over 2 from the left, it's going up to positive infinity, right? Now, we're not coming at it from the left, we're coming at it from the right. So there's actually another one of these little snakes that goes like this, right, and just keeps on moving, right? So if we're coming at it from the right, we're actually going, here, I'll just use a different color here. If we're coming at it from the right, actually, we're going where? We're going down to negative infinity. So either you just can say that you figured it out, or you can just kind of naturally come at it and say, well, because I'm coming from the right, this has got to be negative infinity, even just because of the graph, and that's all. If you want to be super awesome and show that sketch of the graph as almost like work, like, hey, I figured that out, that's what the graph looks like, well, then more power to you, all right? Now, if I may, right, this holds for a bunch of other graphs. Like, let me give you an example of one. Right? Let's say we have the natural log of x. What does that look like? Well, most folks can conjure up that it looks like this, yes? So what often gets asked are things like, what's the limit as we approach x equals 0 from the right? Now, of course, they wouldn't ask from the left because there's nothing over here. But if they ask, what about from the right? You go, well, from the right, it looks like you're coming, yeah, you're just going down to negative infinity. See how that works? You can get there uber fast by just knowing the graph. And so that's going to help in a few instances. Usually the instances in which that helps is like your trig functions and your natural log functions, to be honest with you. Past that, there isn't much that gets used in that arena. Nonetheless, hopefully we agree that that is our answer. Now, the limit as you approach pi over 2 from the right is negative infinity. All right? So the next question within this series that says, what kind of discontinuity is that? That is a what? That is a non-removable discontinuity. It is also called an infinite discontinuity, or it is a vertical asymptote. Remember, so long as at least one side of the limit is headed to positive or negative infinity, we just say that's what's called a vertical asymptote, also called a non-removable discontinuity, also called an infinite discontinuity. All right? Now, that all being said, let's go here and let's evaluate the limit as x approaches 1 of h of x, as well as the limit as x approaches 2 of h of x. And while we're on the topic, what kinds of discontinuities, if any, do we have at x equals 1 and x equals 2? Well, listen to me carefully. For these piecewise functions, if they ask you to evaluate the limit as you approach 1, they're being sneaky. What they really mean to say is, get the limit as we approach 1, both from the left and from the right. Isn't that rude? Because built into the find the limit as x approaches this number is the notion that you're supposed to come at it from the left as well as come at it from the right. Okay? So in this example, let's do that. what is the limit as x approaches 1 from the left of h of x? You see how pretty we write that? Limit as x approaches 1 from the left of h of x is what? Well, let's look. Which piece do we use? The answer is we use the tip-top piece, because that's the guy when x is below 1, and that's x squared minus 1 over x. So I'm simply going to plug in 1 and see how that goes. 1 squared minus 1 over 1. Well, 1 squared is 1. Minus 1 over 1 is minus 1, so that gives us 0. Cool. But while I'm on the topic, what is the limit as x approaches 1 from the right of h of x? Well, a lot of pieces there. Let me take a look. Which piece do I use? Be careful. I don't use this. This is what happens when x is 1. When x is 1, for whatever reason, y is 3. But who cares? That's not what I care about. I care about this. When you are just above 1, when x is slightly greater than 1. So I'm going to use x squared minus 1 to plug in. So x squared minus 1, oh, look at that. It gives you 0. Do we notice that? So the limit as x approaches 1 from the left is this number 0. The limit as x approaches 1 from the right is still the number 0. So what you could do is you can just say, all right, look, because of these two guys agreeing, because they match up, therefore the limit as x approaches 1 of h of x is just 0. I mean, that's the end of that discussion. All right? Now, unfortunately, we're going to do the same nonsense with 2. All right, so let's go ahead and do that now. Hopefully we get the idea. And I'm running out of room here, of course, so I'll write a little tinier. The limit as x approaches 2 from the left of h of x is what? And while I'm at it, let me just kind of kill two birds with one stone. Limit as x approaches 2 from the right of h of x is what? Well, let's see. Limit as x approaches 2 from the left. Now look, be careful. Which piece do you look at if you're coming at 2 from the left? I want to consider numbers which are just below 2. So it's the second from the bottom one. Well, that's just tangent of x, right? So that's going to be tangent of 2. And to be quite frank, that's as good as we're going to get. I mean, really, tangent of 2. I have no idea what that is. Neither do you. Don't worry about it, right? That's as far as you can take it. You just stop and call it a day. Now, what about the limit as x approaches 2 from the right, however? Well, let's take a look at that. From the right, I want to consider numbers which are above 2. So I'm going to use this very, very, very bottom function. And let's see what that gives me. That gives me the ln. Now look, I remember my ln's in cursive as well, as you'll see there, right? Look, this is a limit because I put a little dot there for the I. This is an ln because there's no dot. Subtle, but it matters. So either way, it's a ln, the natural log of the quantity x, which we're going to plop in a 2 there, excuse me, plus e minus 2. Well, that's going to give us the ln of e, yes? Now, what is the ln of e? We have to remember this identity. The ln of e is 1. The ln of e is 1. Now, be careful, though. As you're coming at 2 from the left, you're headed to this number, the tangent of 2, which certainly isn't 1. Coming from the right, you're headed to 1. So, what do you say? If we get a disagreement, we say the limit does not exist. And again, you want to be super awesome. You write, therefore, the limit as x approaches 2 of h of x in general does not exist. Simply because they disagree. From one side, it looks like we're headed to tangent of 2. From the other side, it looks like we're headed to 1. So I'm like, sorry, babe, got nothing. I got nothing for you. Now, all that being said, if we have an issue where the limit doesn't exist, that's likely the cause, that's likely the result of a discontinuity. So let's go over for these two. What kinds of discontinuities, if any, do we have at 1 and 2? The one on the bottom, I believe, in other words, the one at x equals 2, is a bit more obvious. If you take the limit as you go from the right and you're headed to some number, but then from the left it is from some entirely different number, like couldn't be more off, we have a name for that. It is called a jump. And a jump is yet another brand of non-removable discontinuities. A jump is but another brand of non-removable discontinuities, okay? So the two types of non-removables are what? Yep, we got ourselves jumps and we got asymptotes, broadly speaking. Okay? Now what about this guy though? The top one's weird. And I'll give you the answer right now just because I know you're just waiting on the edge of your seat. The answer is it's what? It's actually a hole. This is what a hole looks like in piecewise town. Okay? A hole is what happens when the limit as you approach a number from one direction is the exact same as the limit as you approach it from some other direction. But look at this. Look very, very carefully at the details. If you come at 1 from the left, we figured out this nonsense is 0. If you come at 1 from the right, we figured out this nonsense is also 0. But strangely enough, when you slap into 1, you get 3. Do we notice that? So coming at 1 from one side, we get a number. That's 0 in this case. Coming at 1 from the other side, we get a number, which again is 0. But when you hit 1, shit just goes bananas. And so as a result, what do we call that? We call it a hole, which again is a type of what? Removable discontinuity. Now, I should point this out. Excuse me, I should point this out that if I took this part of the piecewise function and it wasn't there, I'm going to get rid of that entirely. That still doesn't change my answer because as I come from the left, it's still 1. As I come from the left, it's still 0. As I come from the right, it's 0. It's just that at that point, it's actually not defined at all. Cool? So if it's either not defined at all or it's defined at a number that disagrees with the previous two, we call that, so sorry, that's a hole. All right? Now, that brings up an interesting point, though. No pun intended. What if we could ask this? How can we either define h of x at any of those points of discontinuity to make it continuous at those points? The only continuity issue that is fixable is one that is removable. In other words, the only place at which we could even consider this is at x equals 1. So let's see what happens. At x equals 1, what do? Check it out. It's really, really simple. You just man up and you say, let's define h of 1 to be 0. Like legitimately, you put the hammer down and have the authority to say, yep, I'm going to define h of 1 to be 0, and that's all there is to it. End of discussion. Why? Look, because the limit as you approach 1 from the left is 0. Limit as you approach 1 from the right is 0. There's just this silliness that when you hit 1, it goes to 3, which is stupid. So just fix that, which I just did, and therefore we have made this function continuous at that point. Everything else, not fixable.